Okay, so we're talking about power now. It is technically the derivative of the work done. And you have to be very careful because all these terms kind of mesh together and then can become confusing. But the book defines power as the rate of change of the energy in the system in time. Okay, so for us, we're not dealing with heat yet, and heat does show up in power, but since we're not dealing with heat yet, it reduces to the derivative of the work done by the over the change in time. So the work is the respect of the change in energy of the system. Remember, we went through this kind of lengthy process where the change in the energy of the system is expressed by the work done by conservative forces plus the work done by dissipative forces plus the work done by external forces, right? The conservative forces being your gravity and your spring force, and the dissipative forces being like the friction and the drag. I was going to say viscosity, but that is a little bit different. It's related to drag. So, and then the external forces, those are like your tensions and your thrusts and your ropes and your pulleys and your pushes and your pulls and your external forces, right? And we were able to kind of quickly show that the work done by the conservative forces is equal to the negative in the change of the potential energy. The work done by dissipative forces is expressed as negative of the increase in thermal energy, and that dissipative or external forces thing just stays on its own. So that's the energy in the system. It's equal, because there's kinetic energy as well right there, right? That equals minus delta K, and it's a big helpful thing to combine all these into an initial and final thing to get a dissipation or a general conservation of energy formula. So I'm going to cut those. Okay, so that is the work done. Now, if the force is constant, right, this can be expressed. The work is obviously the dot product of force and displacement. And so if force is constant, then this just equals F dotted with the time derivative of the displacement. We just get V. That's if the force is constant. If it's not constant, then you have to replace this with an integral. And it's a really kind of fun problem where you have the what does it even mean to turn this equation into an integral? Well, in the same way that the work is equal to the integral of the force over the displacement, you can say the power is the integral of the force with respect to those velocities from an initial to final velocity. And so you see this lends itself very well to, among other things, drag, right? And the drag force, if the drag force is constant, it depends on velocity, like in the case of linear drag and the case of quadratic drag. Other times it is just straight up constant. And I want to talk a little bit more about this. Another way to write power is in terms of integrating the energy with respect to time, actually. Okay, you can also express the power, if you can, well, let me write it this way. You can express the change in energy of the system as the integral of power with respect to time. And that actually ends up being an interesting result as well. A cool application of this is horsepower. We can model different, okay, by the way, I'm assuming that folks know that the units of power would be joules per second, which is a watt, right? So 1 watt is a joule per second. And so that's that's the SI unit for power. Obviously, BTUs and horsepower, these units are a little bit better for industry. Well, watts is pretty helpful too, but a horsepower is equivalent to like 760 or so watts. I think that's the conversion. Double check that. But what I wanted to do is kind of show you with this integral, with the integral of integrating power over time to get change in energy, I can show you the, because sometimes you might know the power output and not anything about the forces. For instance, car speeds up at constant horsepower. Okay, this is one way to model car, bad car, but so if it starts off from rest, initial velocity is 0 and a constant horsepower, right? Then obviously after it's gone some distance, it's going to have some speed. Don't mind the circles, right? You can find the final speed given the horsepower by integrating it over time. And so if you integrate a constant horsepower with respect to time, you're just going to get PT, and that will equal change in the energy of the system, which in this case, ignoring friction, is just kinetic energy. So this just equals K final minus K initial, which, you know, can start off at 0. And so look what we get. We get an equation of a PT equals 1/2 mv squared. And if you solve for V, then you actually recover a formula in a question that we had in chapter 2, way back in the very beginning, where the velocity squared was equal to twice the horsepower over the mass times of the car times T. Remember this problem? It was, I think it's 2.76, something along those lines, where we had, where this was an example where we had a car that was starting from rest with a constant horsepower. And so evidently constant horsepower or constant power output does not give us a constant velocity and time graph. It gives us a velocity in time that is increasing as the square root. So that graph is obviously V, the function of T, something like that. This is like square root of T with constants on it, right? And so you can start to look at problems, get a more accurate picture of the velocity versus time when you start to vary this horsepower a little bit, right? If you let this horsepower change in time, then you have a more non-trivial integral. And there's really interesting graphs out there that look at the horsepower versus time of a car that's speeding up, from 0 to 70 in a matter of seconds. And you can relate the amount of horsepower to other things in the transmission, like these gear ratios and stuff, and get a more accurate picture of the motion of a car, right? Because one of the first things we start off with is assuming that the car has a constant acceleration from a constant force. What does that do for the force in this case? If the horsepower is constant, what does the force look like in time? And well, you can show that probably the easiest way that I would consider that is to take a derivative of this formula, multiply it by mass. You get a force as a function of time that is decreasing according to 1 over, basically the force is, let's see, if you work it out, solve this for, take the square root and then, let's see, take the square root and divide, or take the square root and then take the derivative. It'll be that the force equals square root of the mass times the power over 2t. And this is actually a good opportunity to check your units. Joules per second, there's a squared, and that's going to cancel with the, that'll cancel with the mass. And so, you have to justify this formula. So evidently a constant horsepower in time will give you a force that is decreasing in time. And why that is, why is the force decreasing to keep a constant horsepower? You might argue that, well, the amount of power depends on the speed. As the speed increases, the amount of force needed to keep the horsepower constant decreases. So these two are inversely related. And sure enough, if you multiply these two graphs together, you should get P, right? Yeah, you should get P. You can multiply these two graphs. So you may encounter this in the future where you have a power problem where you're given a horsepower and know nothing about the force. One other example in the textbook is about a bicyclist, and this is a horsepower. Yeah, it's a horsepower problem, but it's just a power problem where the bicyclist is going, I'm just going to draw the box. Drawing a bicycle can get kind of cumbersome. And we're trying to figure out how much energy the bicyclist is burning as he or she is pedaling at a constant speed, right? So there's a drag force and there's an applied force and they equal. And so the power output, the mechanical power output now, is equal to the magnitude of it, because power is a scalar, just like work is. It's the dot product, well, it's technically the dot product of the force with the velocity. So drag has a minus power, but we're just talking about the magnitude, since it just ends up being the drag force times the velocity, which in the textbook, this problem, you calculate the drag force with the quadratic drag model. How do you know which one to use in which circumstance? You are most likely given when to do it. That's so, and most of these problems, unless explicitly stated, we assume a quadratic drag force. So this is the mechanical power that is required to keep the bicyclist moving at a certain speed for a certain amount of, certain speed, given those conditions. Now, what then they go next is to say that the mechanical power exerted by the cyclist is only a fraction of the change in energy of the cyclist because of metabolism. And they go into a little bit of details about metabolism. It's kind of interesting. They make an assumption that the mechanical power is equal to 25% of the total metabolic power, right? So you look at, the typical nutrition information that you find on food for 2,000 calories per day, that is a unit of power, right? That's a typical power output that human beings have. Most of that goes to internal processes to maintain a constant temperature, right? For involuntary biological processes to take place, breathing, blinking, all this other stuff that you're not in control of. But there's some fraction that's available for actual motion and movement and jumping up and down and, throwing javelins and riding bicycles and shooting basketballs. And so they do a simple model and say that the metabolic power or the mechanical power output that's possible is about, basically this is like an efficiency, that they say that the human body is quote unquote 25% efficient. And so, the mechanical power then is 1/4 that of the metabolic power. My fault. So that's another question that shows up in the book about power.